Hello, I'm Skylar. I'm going to be presenting our EMNLP paper, StyleRemix, Interpretable Authorship Obfuscation via Distillation and Perturbation of Style Elements. So our task in this paper is authorship obfuscation. What is authorship obfuscation? It's rewriting text to obscure the original author's identity. So you can see this has a lot of applications in high-stakes situations where we don't want text to be traced back to the original author. In this example, we have an original text from Obama, and an example of an authorship obfuscation might look like this, where we're not able to see who the original author was. The issue with previous methods is that they're one-size-fits-all. Additionally, they also lack controllability and explainability. It's not really clear what's going on under the hood. You just get an input and an output. So in our work, we identify that there's a need for an obfuscation method which can solve this, being explainable and steerable, while also being effective compared to other baseline methods. Our paper introduces StyleRemix with the intuition of, can we obfuscate text by modifying specific style elements? This could be something like length or the formality within the text. More specifically, we define the following style elements. So in the center of the screen, we have a presidential speech. What are some different style elements that we could manipulate to get a different text? One that we identify is improving or increasing the grade level. Another one is making it longer, or increasing the sarcasm, or making it more formal, or changing the intent to be more of a narrative, increasing the function words, or changing the voice from active to passive. For all of these, we can also manipulate these specific style elements in the opposite direction. For example, we could make the length lower, or make the grade level lower as well, or make the formality lower. In total, we identified these 7 distinct style elements with 16 different style directions encompassed by them. Now I'll introduce our method StyleRemix, which is composed of 3 parts. Here I'm going to introduce style axis data, which is collecting data for the 7 style axes we introduced in the previous slide. How do we do this? We take existing text from online, such as Wikipedia, blogs, and books, and we're going to rewrite them with a language model towards each of the style axes that we defined. So in green we have sarcasm, in orange we have formality, and we have the rest of our style axes as well. What we do is we pass in the input into the language model and ask it to make a more and less sarcastic version of the input text. We also can do this to get more and less formal versions of the text. Once we have this data and we filter for quality, we can train style models. Specifically, we can first obtain adapters, which are lightweight modules that will allow us to rewrite input text to be more or less sarcastic. We can also do the same thing for formality. Finally, we also might want to train classifiers to tell for next parts of our method whether text is sarcastic or not. Same thing for formality and for all the other style axes. Overall, the data that we collect here is a valuable resource to the community. It can be used for future explorations into style axes. Next, I'll talk about part 2 of our method, author style data. So here we want to assess how do author texts differ with respect to the style axes that we just defined. So what does this look like? First, we collect text from a specific author. Now we're going to use the style classifiers which we just defined in the previous slide. So for example, green would be sarcasm and the orange one would be formality. We're going to put the text through and we're going to get an average author style vector. So in this case, since the scores are from 0 to 1, we can say that this author has a low level of sarcasm while they have a high level of formality. We're going to repeat this procedure for other authors, collecting their data, putting them through the classifier, and getting their average author vector so that we can see how do authors' texts look like with respect to different style elements. The collection of text that we collect from different authors is a valuable resource for future work in authorship obfuscation as well. We denote this AuthorMix. Now I'll talk about the final stage of our pipeline, the actual obfuscation itself. So given an input from a specific author, we can collect the author style vector from the slide before. Alternatively, we could actually calculate the style vector for this specific text rather than just the author. We're also going to retrieve the mean style vector, which is found by ensembling and averaging the style vector for all the authors in the corpus. Next, we're going to take the difference and see how much does this author's style vector differ from the mean. The intuition here is that we want to identify the specific style elements that this author is over or underrepresenting. So in this case, we can see since green corresponds to sarcasm, this author has slightly lower sarcasm than average, and since orange represents formality, they have much higher formality than the average author. Now that we have this difference vector, we're going to use a base language model which can rewrite texts, and we're going to plug in the adapters corresponding to this difference vector. So in this case, we're going to use the green adapter with a blue up arrow to indicate that we want to increase the sarcasm in the rewrite. We're also going to use the orange adapter, indicating the formality adapter, with the red down arrow to indicate that we want to decrease the formality in the rewrite. And we can repeat this for all the other style elements. Finally, we're going to pass the input back into the base language model, plus these adapters. After doing this, we're going to obtain a rewrite which takes into consideration the different adapters and obfuscates the text effectively and with high explainability. So next, I'll summarize the datasets that we release as part of this work. For one, we have the Distilled Style Components dataset, or DISC, which is a set of web, book, and blog texts rewritten towards 16 distinct style directions across the 7 style axes that we identified. We also have AuthorMix, which is a set of texts from 14 distinct authors spanning 4 domains: presidential speeches, novels, scholarly articles, and blogs. DISC is used to train our style adapters, which we can use in StyleRemix. AuthorMix is used for evaluation. Specifically, with respect to each of the 4 domains, we want to see how well do StyleRemix and other baselines obfuscate texts from different authors. So how do we actually evaluate how well our obfuscations are doing? So authorship obfuscation is traditionally evaluated using automatic metrics on 3 criteria. Obfuscation, which is saying how well does our rewritten text obfuscate the author style. Fluency, which is assessing is the rewritten text still readable and fluent. And meaning similarity. We want there to be a preservation of the meaning between the original text and the rewritten text. Finally, following previous work in style transfer and authorship obfuscation, we have an aggregate quantity of obfuscation, fluency, and meaning similarity, which gives us an overall score. So the ideal obfuscation should be high in all 3 of these categories to get a high overall score. So now I'll go into our results, and this is on a specific subset of AuthorMix, blog. For the full results, see the full paper. Here we show the obfuscation results on this data set with our method in green and all the baselines in other colors. Specifically, we have 2 types of baselines: instruction tune models and other obfuscation baselines such as Jamdeck, stylometric, and machine translation. We also have our similarity, fluency, and overall metrics. What are the takeaways? Well, we see that StyleRemix beats all other baselines in both obfuscation and overall obfuscation quality, while remaining competitive with respect to similarity and fluency. And this is pretty impressive considering that we're going against other state-of-the-art obfuscation baselines such as Jamdeck, as well as instruction tune models of much larger size, such as 7dB Llama 3 instruction, while our model is only a Llama 3 8B model. We also have results from human evaluation. Specifically, we have grammar and fluency, in which we remain competitive, as shown as on the right bar. We also have 2 questions regarding meaning similarity, which show that we are second highest. And finally, echoing the results from the previous slide, we're winning in obfuscation and overall obfuscation quality with respect to all other baselines, including the much larger Llama 3 7dB. Thank you. That concludes my presentation. Please check out the paper for the full details.